All right, guys, we're going to start looking at section 10.3. We're going to break this one up over 2 lessons as well. So let me start going through some of these guys for you. So focus on this one is going to have now a lot to do with more like specific statistics that you guys are going to definitely be familiar with. Things like mean, median, mode, standard deviation, a lot of what you've heard of before. One part that may be new to you will be the normal distribution stuff. That's going to come up in part 2 of this lesson. We're going to spend a little more time on that one, so that's why I'm breaking this one up into 2 lessons. But in either case, this is going to be heavily reliant on technology for doing this kind of stuff. We rarely calculate statistical data by hand anymore, so it's just too easy to do it with other tools. So here's the first thing we got to take a look at. And this is important, so pay attention to this. You're going to be asked about this. So the difference between a statistic and a parameter. So a statistic is a calculated result from a specific group, right? And so if I were to just say, just do a survey of the students in our class, and I was to find out that exactly 11% of you guys drive red cars. Right, and so that would be a statistic, right? It was a specific statistic from a certain group of people. A parameter is more of a general claim about an entire population, right? And so if I was just to say that on average, 8% of all people drive red cars, right? That would be more of a parameter, okay? And so that's just kind of understand the difference between those two. Let me jump down to one of our specific items of data that we're going to talk about is the median. I'm sure you guys have heard of this before, but we know the median as the middle. So we always associate the word middle with the word median. So if you were to identify a median, you'd want to make sure that your numbers were put in order from least to greatest. Then you could identify the middle value. If there's 2 middle values, because you have an even set of numbers, then we would take the average of the middle 2, right? So let me give you an example from our next page here. So on this one, we have some more baseball statistics. Apparently, this book was really a big fan of baseball statistics, but I'm talking about Roger Maris, for those of you who know who that is. So home run statistics for this guy looked like this. And so if we did want to find the median value, first thing that we would have to do is we would have to put the numbers in order from least to greatest. So this was all the data that they gave us up there. We'd first have to put it in order from least to greatest, and then we could identify the middle number. Now in this case, there's an even amount of values. There's 12 pieces of data, right? So 1, 2, 3, 4, 5, 6. So as I look at this, terms 6 and 7 would be the 2 middle values because there is no true middle. Right in here would be the split between the bottom 6 and the top 6. So we're just simply looking for the average between 16 and 23. So you add them up, divide by 2, and that becomes the median, the middle number. All right, let me keep it going. As far as the 5-number summary, you've probably seen a box plot in the past. You might have called it a box and whisker plot. I think when you see it, it'll look familiar if you don't remember what I'm telling you right now. But a box and whisker plot contains the 5-number summary. Okay, it's got a min and a maximum. The min and the max make up the whiskers, so you'll see here in a minute. And then the box in the middle is made up of these 3 points: the lower quartile, the median, and the upper quartile. Or the third quartile, same thing. The lower quartile represents the value for the bottom 25% of the data. From the lower quartile to the median would represent the next 25% of your data. From the median to the upper quartile would be the next 25% of your data. And then from the upper quartile to the maximum would represent your fourth, like your last 25% of your data. So that's why these guys are called quartiles, is because your data gets broken down into 25% groups. So where they get the lower quartile if you were to take the median of your data, remember the median breaks your data up into the middle value. So you'll then see what the bottom half is and the top half. Okay, and so if you were to do that, the median of the bottom half would be your lower quartile. The median of the upper half would be your third quartile or your upper quartile. And so that's where those guys come from, but it's those 5 pieces of data that help us create a box and whisker plot or a box plot. So I'm going to show you guys how to do this. So you can do this in a calculator. I'll do it real quick in here so you can see it. So if you're going to do it in a graphing calculator, right here you're going to punch the button that says stat, and this comes up for you. And we want edit, so just hit enter. And you're going to see all your list of data. We're simply going to type in that big list of data right there. So I'll do that real quick. So I just created all my list of data, so I just typed in all those numbers. Now I'm going to go back to stat. We're going to go to the right under calculations. These are one variable statistics. So hit enter. Under list 1, you'll notice when we went to edit, notice we just put our data under the title of list 1. So when you now do your one variable statistics, we want to make sure that they recognize, yep, our list is under list 1. We did not have a frequency list, so we can leave that empty. And here we go. So this gives you a ton of information. So right up here at the very top, you have the mean. So that's the mean. We have our sample standard deviation and our population standard deviation. We'll talk about those later. So let me scroll down to the 5-number summary. It's the bottom 5 numbers. So you got your min, lower quartile, median, upper quartile, and max. And that's it. So those are your 5-number summary. With those, we're going to make a box and whisker plot, which I'll show you in a second. So that's if you're doing it on a graphing calculator. In Desmos, here's how this goes. So I'm just going to take this list and type it into Desmos. Let me show you something though. There's really a couple different ways you can do this. I'm going to show you the way that I would recommend. And if you end up with a different way of doing it, then totally fine. So I'm just going to identify my list. So I'm going to say L equals, and hard brackets, square brackets, and I'm going to put in my list of data. So I'm going to type in the same list that we just used. And there's a 5 at the end. Just make sure I get them all. Oops. Let me get my comma in there. That makes more sense. Did I get them all in there? So the reason I give it a title is so now I can do whatever I want with this list, right? Because you might want to do multiple things. You might want to get your 5-number summary. You might want to make a box plot with it, and you don't want to retype the numbers every time you want to use them. So if you just give them a title, like L, then you can tell Desmos to do whatever you want with L, and it automatically uses that list. So let's just say you wanted your 5-number summary. Type the word stats, and then in parentheses put L, and there you go. So there's our 5-number summary. Hopefully the same one we were just looking at on the calculator. Let's just say you wanted a box plot. So let's do a box plot with L. And so again, that's why I give it a title. I don't want to have to retype all this. I guess you could copy and paste it, but here's what your box and whisker plot looks like, or your box plot. So the 5 pieces of data from right here make up this box plot. So you have your minimum right here at 5. That's the left whisker. The box that you see in the middle goes from Q1 to Q3. Right, that's those values. Right here represents the median. So you have 3 vertical lines. We draw a vertical line for Q1, we draw a vertical line for the median, and a vertical line for Q3. Right, and if you kind of connect across the top and bottom on that, you get the box for your box plot. And then on the far right, you have your maximum, which in this case was 61. Guys, you might notice on this one that 61 which is right there, is pretty far outside of the group, right? It's quite a bit bigger than any other number, right? It's not really close to anything. So we might identify 61 as what we call an outlier. And oftentimes we like to exclude outliers. So what you're seeing on this is a true box and whisker plot. We will also have what you call a modified box and whisker plot where you get rid of the outliers. So right here, see how it says exclude outliers? So if you click on that, then here is the box and whisker plot that we would call a modified box plot because we got rid of the outliers to make the data a little more relevant to the main numbers that are in the list. So how do we identify an outlier? Like, how do we know if 61 should be considered an outlier or not? We're going to talk about that a little bit later. Okay, so but anyway, if you don't check this, it's a box plot. If you do check it, it's a modified box plot. And oftentimes, right here, you'll see how they still put a dot right there for 61 because they're still showing that that was a piece of data, but they didn't want to include it within the main numbers within the box plot. So it's still represented on the graph, but they just didn't draw the whisker all the way out to it. So that's something we need to be familiar with. Let me take you back to this guy. So this was their version of the box plot. These are based on a different set of data, though. What I just wanted you to see in this diagram is making sure you recognize what all the 5 main points represent. Okay, so you have your minimum and your maximum at the ends, and then again you have Q1, the median, and Q3. Now, one thing I wanted to point out on this is remember this is all separated into quartiles, 25% groups. So that means 25% of my data is from here to here. The next 25% of my data goes from here to here, and then I have 25% from the median to Q3, and then 25% from Q3 to the max. So I'll give you a quick example. Let's just say that these numbers represented the amount of money that you made each week for the last 40 weeks. So in other words, this represents 40 pieces of data, right? If each week is one element of data here. Okay, and so what that would mean is for 10 of the weeks, so if I had 40 weeks, I'm dividing those by 4. So for 10 of the weeks, I made somewhere between, I don't know, I'm guessing here, $59 and $64. So that represents 10 of the weeks. From 64 to whatever that is, let's say 68. That was another 10 weeks worth of income. Again, this would represent another 10 weeks, and then from Q3 to the max, whatever those numbers are, would also represent 10 weeks of income. So you're taking your however many pieces of data value you have, dividing them by 4, and that's what goes into those sections of the box plot. All right, let me keep it moving. All right, so if we wanted to compare box plots, obviously you could put these onto the same graph and then make some comparisons, right? So that's typically what this stuff is used for, is when we gather data. We may want to compare certain data values together. So if I wanted to compare the life expectancy of males to life expectancy of females, one way to make that comparison would be to make 2 box plots and then look and see what stands out to you within those box plots. So let me do that real quick so you can see what it looks like. So I went to Desmos and created a box plot for the top row. This was the males, and then here's a box plot for the bottom row, which was females. Let's just not worry about outliers for a minute. Let's get these guys separated. So I'm going to change my offset here. There we go. All right, so there's my 2 box plots. Now we could look to make some obvious comparisons. Remember the black one here is the males and the red one is females. So right off the bat, you might say, hey, females tend to live longer. So, and that's statistically true. Compare the maximums, compare the minimums. But it's a great way of seeing the obvious differences once you put it into a graph. as I looked at the list of data for these, I didn't really notice an outlier, so I'm not sure this would change. Yeah, so that didn't change, and that didn't change. So even though I'm clicking exclude outliers, it doesn't look like there were any. So so it didn't affect my graphs at all. So let's talk about outliers without a crooked camera. All right, so how do we identify whether or not something is an outlier? Now, if you look at all those numbers, they're all very close together. So I didn't expect to get any outliers from that one, but let's see how we would identify them if we had one. So I will show you a real number example in just a minute, but let's just say here is my box plot. Here's my median. So remember, this is your lower quartile, this is your upper quartile. And if you were to take this number minus this number, you get what they call the inner quartile range. So the inner quartile range, again, is just the range of those two quartiles. Okay, so we're going to subtract those to get the inner quartile range. Multiply that by 1.5. That's going to give you some number, right? So whatever that number is, a specific piece of data, if it is that much below the lower quartile or that much above the third quartile, it's considered an outlier. Let me show you one with real numbers. I just wanted to explain what the inner quartile range was. All right, so here was some data. And this is one we talked about it a minute ago. There's that 61 that we were seeing as an outlier, and even Desmos identified that as an outlier. Okay, and so this was the 5-number summary. So this was the minimum, that's Q1, the median, Q3, the maximum. Okay, and so using the little formula you guys saw on the other page, the inner quartile range would be Q3 minus Q1, and they got 19.5. They're going to multiply that 19.5 times 1.5. And if you just took that step, this is what you would get, right? You would get 29.25, which means here's my lower quartile, if any value is more than 29.25 below 11, or more than 29.25 above 30.5, then it's considered an outlier. Okay, and so if you look at what they did down here, they said 30.5 plus that number that we just calculated gives me that amount right there. So any number above this is considered an outlier. So there, of course, 61 is above that, so it's considered an outlier. And now you could look to do it as a modified box plot where you sort of just put a point on the outlier, but you treat the next number down as your maximum, right? So the new maximum became 39. All right. One that I know you guys are all familiar with is the mean, right? The mean is the average, as we know, and a basic mean is just add up all the data and then divide it by the number of elements that you just added, right? So there's our basic mean. It's always funny to me. It's such a simple formula, and they always write it with such complex looking values and symbols. It looks more complicated than it really is. So as far as computing a mean, again, not something we're going to be doing by hand, really. You should understand the formula for how a mean works, because there can be certain times where you're asked about steps within calculating the mean, but in general, we're going to be using some technology for doing stuff like this. So if you were doing it with a graphing calculator, I'll show you this really quick. Again, you would put in your list of data like we did before. Remember, the mean was already on the screen that we saw. When you went to calc and you went to one variable statistics, the mean was the number at the top. The little X with the line on top, that's the mean. So 22.9 was the mean of that data. Okay, so really simple. If you want to do this in Desmos, you can literally type in the word mean for your data. Hold on, I have to change my symbol at the end. Oh, there we go. I have to change these two parentheses. This is why, like I said before, I like just giving it a title, because then you don't have to worry about all these kinds of symbols and stuff. But anyway, so I literally typed in the word mean, and then in parentheses I put my list of data. There's the mean. All right, so real simple on that. So we can certainly use technology for calculating our specific statistics. All right, let's talk about a weighted mean. So I know you guys would at least have some understanding of a weighted mean, because usually that's how your grades are figured out. Like especially in my class, I use weighted averages for my grades. I have category weights. So like your category of testing grades has a higher weight than, say, your homework category. Okay, and so this is what we're seeing as far as using category weights. Mainly what you're seeing in this formula is, if I wanted to find a weighted mean, this is like if I had certain elements with certain frequencies. So like, let's just say you had a list of 3 5s, 4 7s, 1 6, whatever. That's what these guys represent. So it's like, this is the specific data value, and this is how many of those you have. Okay, so it's like if I had 3 5s, I could write this as 5 is my data value, and I have 3 of those, so 5 times 3, right? Instead of having them listed out individually. And then, of course, the denominator is how many elements you have, so that would just be the sum of your frequencies. Remember, this little Greek symbol for sigma always represents a sum. So this is just the sum of your frequencies. So let me give you a word problem here. I know you guys love word problems. All right, weighted mean. All right, so final exam must account for 25% of the semester grade. So that's its weight. That's its category weight. He has an 88.5 going into the final. What's the minimum score needed to earn a 90 for the semester? This is like right out of something you guys would do, right? So this is his preliminary average, and it was initially had a weight of 75%, right? Because the final exam has the remaining 25%. So those are the two weights. So this is what he has, and that's on this weight. And then we have whatever he gets on the final, which is X, that's what we don't know, times this weight. Okay, and so that's what we're shooting to see what will give him a result of 90. Or in this case, they're saying 89.5 because that would round up to a 90. So what does he need to get in order to get an 89.5, which would give him that A? So let me show you this guy. So here's just the basic layout of this. Really not needing the denominator here. That's going to always total 1, but it just kind of shows that we did account for all of the weight that would go into this. It should add up to 1, but anyway, so it's really not going to change our answer on this, but this was his current score times its weight. Here's the final exam score times its weight, and we know that he needs the end result to be 89.5. Right, and so then it's just very basic algebra to solve for x, so he needs a 92.5 on the final to get what he needs. Right, so pretty basic. That's how the grades in my class work. So with those weights, we can always calculate in that way. All right, so that's going to be it for part 1. Next one, we'll get into standard deviation for part 2.